I've been kind of teasing fluid simulations as Vertex Animation Textures in my recent OpenVAT content, and although you can do this yourself, I thought it required some explanation. I've included an experimental folder in GitHub, and you can find this in the link in the description, where you'll find some files and tools that contain all of the geometry node groups that we'll be using in this video, as well as some helpful scripts. There will be a template file with these scripts registered directly into the file. So when you open it, you'll just have to say, okay, to run the Python. Stick with me on this one. It's dense, but I guarantee you'll learn something. So I've come up with two different methods to encode these types of simulations into Vertex Animation Textures. The first one we call a triangle soup. So we can think of this like creating a bank of triangles. We'll need the maximum amount of triangles that exist in that simulation over time. And they can all be stacked on top of each other identically. So for the purpose of this example, I'm going to break it down to the simplest possible form. We have our bank of triangles, which obviously have 3 verts. And we have our simulation, which for this example is just a plane, which has 4 verts. So our first step will be to break the simulation into triangles or triangulate it. And now we know that our simulation consists of 2 triangles. We'll break the simulation out into these 2 separate triangles as instances, and then we'll grab from our bank. And then from our bank of triangles, we'll map each vertex into the vertex position for each one of these instances. So since this is just a simple plane, all we need is 2 triangles in our bank, and then vertex 0, 1, and 2 get mapped to 0, 1, and 2. And then for the second index, the same thing happens. Let's say we have 0, 1, and 2. So what was 4 verts in our original simulation becomes 6 vertices. And what was 1 face becomes 2 faces. Now, if you pay attention to what I drew here, you'll notice that if I did have a front face and a back face of this triangle from the bank, and let's say this is facing forward towards the camera right now, you'll notice when I map vertices 0, 1, and 2 to 0, 1, and 2 in this triangle, that this triangle will actually be flipped upside down. Our triangle of the second index will be facing the correct direction. So there is some nuance to this. When we map each triangle to the simulation, we need a way to register if the triangle is facing forwards or the way we want it or backwards. When it's detected that a face is facing backwards, we need to remap 0, 1, and 2 to swap these 2 positions of 1 and 2. So vertex order then becomes 0, 2 to 1, and then this face ends up being mapped correctly. I'll show you this in geometry nodes in a second. Another issue arises with this too, because where we used to have a connected face here, I separated these in this drawing just to illustrate a point. But these 2 verts and these 2 verts will literally be on top of each other, meaning that this center line is shared between them. So if this edge is a soft edge, it becomes a hard edge when we encode it. And this has been the major reason that has stopped me from talking about this before. But now in Blender 4.5, we can set the normal based on the vertex. So all we have to do is store the vertex normal of these 2 vertices when it's still connected. And we transfer that connected normal to each of these vertices. So now, even though that these are 2 separate faces, if we had smoothing on this edge, because of the normal facing direction of the vertex, will now be preserved. And you can see this is already getting pretty complicated, but we have one more step we need to think about, which is the deformation basis. Imagine this is a mesh that we're encoding, and we'll say our origin of 0, 0, 0 is right here. If we use a start frame, and let's say that this is frame 1. If we use this start frame for the deformation basis, it will be relative to this original starting point. If we use the starting frame, frame 1, for this deformation basis, the way that this gets quantized for each vertex becomes different. So the movement of this vertex on the grid might be different than this vertex, for example. So the way that we can solve this is using a custom deformation basis, which is an option in OpenVAT. You can use the selected object as the deformation basis. We can take this entire object, duplicate it, and move all of its vertices to 0, 0, 0. So what we end up with is an object that just looks like a single vertex. Everything is contained into that original space. Then when we encode, the position of the vertices that are matched up at the corners have the same quantization over the grid. And this is really important because if we don't do this step, we'll have gaps wherever we have two overlapping vertices. They might not move the same exact amount, especially if we don't encode a 32-bit texture. This can be super apparent in the resulting mesh, and you get giant gaps between each triangle that's reconstructing the mesh. And the final thing to think about here is we might have a bank of, let's say, 5,000 to make up the faces in a simulation. Well, you should know that those 5,000 triangles becomes 15,000 vertices. So the simulation becomes pretty heavy in vertex count inherently just based off of this. And at any point in the simulation, you probably have less than this full count of faces. This represents the maximum count over time. So you might only have 50 faces in the simulation at a time. And we don't want this bank just sitting around here at 0, 0, 0. So anything that isn't being currently used in the simulation should collapse its vertices into 0, 0, 0 to basically give it 0 scale and 0 face area so that when this is in engine, that this does not appear. So a quick little recap here. The first step that we have to do with the triangle soup method is split our simulation into triangles. Our second step is we have to determine the maximum amount of faces in that simulation. Step 3 would be to take that determined max amount of faces and make a triangle soup containing that amount of faces. Our fourth step is to reconstruct that simulation out of that soup. Our fifth step is to fix the face orientation of any triangle that is mapped backwards onto the simulation. And our sixth step would be to transfer the normals from our simulation onto the reconstructed representation of the simulation. So let's get into an actual example. This was encoded using a triangle soup, and it looks pretty good in here in Blender. It also looks pretty decent in Unity. Now I'm using a pretty shiny texture here, so it's highlighting some of the triangles that are not completely smoothed out. There's a little improvement in the shader that can still happen, and this is still experimental, so we can't expect perfect results when we run this, but I would say this is pretty passable for what it is. And just for your information, this is around 64 frames. And the final texture here ends up being 2048 by 2048. So it's not too crazy. I wouldn't say it's necessarily mobile friendly. You would want to be smart about how you use it and use it in small cases where you really need it. Think of like a waterfall splashing. You might use this kind of technique for the actual splash, but the waterfall itself could just be made of planes that are deforming with the texture that's sweeping over it, maybe using flow maps. So let's get into how this was actually made. So this is the actual object that I encoded from, and we'll get into this geometry node setup in a second here. This is what I was talking about with the deformation basis. So this contains our full count of triangles, which in this case is 13,786, which gives us 41,358 verts. But they're all collapsed down to 0, 0, 0. There's a lot going on in these geometry nodes, but you can see we're referencing the collection reduction. So in this reduction collection, I have an object called reduced, and you can see we have a modifier stack here. The first modifier just references the full baked simulation. So this is with all of the vertices intact, and it realizes the instances. Then we have a decimate modifier, with a ratio of 0.05. So even though we have so many vertices in our reconstruction, this is around 5% of the original simulation's total vertex count. And under this decimate modifier, I have one more geometry node group. If I turn off this modifier, you'll see that the simulation creates a lot of vertices on the bottom of this mesh. So this geometry node group just checks for an object named bounds, which I have an object named bounds, you can see here. And it raycasts from each face's normal facing direction, just a very small amount. And if it hits that bounds, it is culled from the simulation. So this saves us a lot of vertices. I think it ended up being like 15,000 or something that this cut down when I added this. And you can see it's not the greatest looking thing here. For one, this isn't smooth. And on top of this, you can see because we're only using 5% of the original simulation, the quality here is reduced a lot. And that's just so we can have that reasonable size when we encode our Vertex Animation Texture. So that's the full modifier stack for this reduced object. And then in our reconstructed object, we're taking that reduction and we're following the steps that I outlined in the triangle soup model. So we are constructing a triangle soup. The way that I'm doing this here is just creating a grid with 2 vertices by 2 vertices, triangulating it, and taking the first face of this. So we're getting one triangle. And then we're instancing this on points on a mesh line. This is technically a mesh line, but if I unhide the properties, you can see its start location and its offset are all set to 0. We then realize these instances immediately to get back into the point domain. We then take our collection, which was that reduction collection. We realize its instances and we triangulate it. We then take the triangulated geometry and split 2 instances based on the index and realize these instances. In this section, we're sampling the position from each index of our split collection, and we're transferring it to each index of our triangle soup. This method here is to determine whether those faces are facing the correct direction. We take the true normal of the triangle soup reconstruction and the true normal of the original collection, and we subtract these. Based on whether or not the result of this is equal to 0, instead of using a flip faces node, we're flipping the vertex order using a for each loop. We're basically sampling the position of index 1, and we're setting the position of index 2 based on that position of index 1. And we're doing the same for index 2. We're sampling the position of index 2, and we are setting the position of index 1 based on that position. And this loops through each face that has been identified by this function to do this. We then join the flip faces with the faces that didn't need to be flipped. And this doesn't weld vertices or anything when you join geometry here. This is just combining those into the same geometry stream. And then this is the final step where we set the normal. So we use a sample nearest node here to sample the nearest point in the original geometry. And we sample the normal from that original geometry, and we set it on the reconstructed geometry. So that's basically it. And you can see when I'm scrubbing it in scene here, it's very slow because it's going through so many steps in the dependency graph when it's trying to evaluate this, because it has to read back the full baked sim from that VDB. It has to go through this reduction step, and then finally it has to go through this entire node group to map an entire bank of triangles to that reconstruction. When we encode this in OpenVAT, all of our settings are pretty normal. I'm using a separate map for vertex normals when I encode this. My transform is set to object. I encoded this with the PNG16 method. The most important thing in encoding settings here is I'm not using a single row, because if I was using a single row, you can see this resolution would not be acceptable. But by using a single row, my final resolution is 2048 by 2048. And the other important thing here is I'm using selected object for my deformation basis. And the way that I would do this is make sure that deformation basis is the selected object and reconstructed is the active object. And as long as I have this setting selected, it doesn't matter what frame I'm on, I can encode. Now let's take a look at that encoded result. One disadvantage to this method is we can't blend between frames in this Vertex Animation Texture like we typically can, because it's kind of a toss-up where each vertex will be on each frame. So in between frames, each face is moving to its new position, which might be completely different than its actual position here. So we are locked to the frame rate that we encode in. And this is just playing back at the standard 24 frames per second right now. But still, I think this is a pretty passable fluid simulation, especially for being as light as it is, just being a single 2048 by 2048 PNG 16 texture. The other way I've thought of to encode these simulations is with kind of a SDF method combined with a splatting method. Let me get into what I mean by this. SDF stands for signed distance field. And this is a whole topic in itself, so I'm not going to get into it too much. But so let's imagine another 2D grid here of vertices, just 2D so it's easier to understand right now. If I have something, a circle, inside of this grid, I can use these vertices to determine where this circle is. A signed distance field gives us basically each vertice's representation of its distance from this mesh. And signed in signed distance field just means that we can determine which vertices are inside the mesh and which vertices are outside the mesh. Typically, this is represented as -1 to 1 for any negative value being inside the mesh and any positive value being outside the mesh. So any value between, say, -0.1 and +0.1 represents kind of the edge of the mesh itself. It might be this vertex here, this vertex here, this vertex here. It maybe would pick up this vertex here. So depending on the density of our grid, we can recreate a voxel representation based on a signed distance field. Imagine instead of a 2D grid of points that this is a 3D grid of points. The same rules apply here. And what we actually end up encoding is this signed distance field value for this grid of points itself. So not for the simulation, but for the grid of points that contains the simulation. Let's say this circle moves through this grid of points over time. You could see that all of these vertices would never be used. They'd never be picked up by this -0.1 to 0.1 range. So we need some way to cull these vertices that aren't used. I call this step temporal culling because it is culling anything over time that isn't used in the simulation. You might be able to tell already the problem with encoding a simulation this way is we need a lot of vertices in this grid. So what we end up actually encoding is this signed distance field value for every vertex in the culled grid using a custom attribute. And this will give us basically a voxel representation of our simulation. Because when we play this back, we can grab that -0.1 to 0.1 range, and we can splat or create a plane that faces the camera on each one of these vertices that holds a radial gradient texture. This is kind of representing alpha, so you'd have a full alpha in the center fading out to transparency, so you end up with basically points that face the camera. And we can do this in Engine using Niagara or VFX graph pretty easily. essentially spawning a particle on each one of these points and driving its opacity based on the sign distance field values. But one more interesting thing that we can do here is actually grab the normal. When we project this basically raycast for each one of these points in this grid, we can get the normal hit direction. And if we store this to 3 unique custom attributes, we can encode another map that holds the normal of this splat. So when we reconstruct an engine, we can actually use this for lighting information. Even though it is a series of cards facing the screen, we can fake lighting or normal-based effects based on this normal value. So I have a little geometry node group helper to make this sample volume of vertices that will represent essentially voxels for each vertex. The trick here is we want it dense enough to capture the entire simulation, but we don't want it so dense that we're using way too many vertices. So this grid is about the density that I want, but you can see there's 262,144 vertices in this grid right now, which will be too many to really generate a vertex animation texture. But I don't really need all of these. But to demo what's going on here, I already have a geometry node group on this that is creating the sign distance field. And this is represented in points. So you can see the points here, which are within that negative 0.1 to 0.1 range being represented here. But I'm about to run that temporal culling step. This will run an operation to see if each vertex is within that range. So what I want to do here is reduce the amount of vertices as much as possible before I run that operation, because it's going to be pretty heavy anyway. It has to loop through all the frames and determine if each vertex sign distance field value is within that range. So now that the points are reduced to the size of the sim, I can cull the points over time. I'm going to cut this because it will take 2 to 3 minutes to do. And you can see when that is finished, our modifier has changed some settings in it, which I'll get into in a full video about sign distance fields. But it has this property checked is sparse. And that just means that only the points that we need actually exist in the sign distance field now. But all of them exist all the time. You can see in our representation through the animation, those points in that range around negative 0.1 to 0.1 are being shown here. And in this representation, the size of each point is actually its sign distance field value represented. But now what we need to do is actually encode some values into these points. I'm going to name this collection of vertices SDF capture. And I'm going to change the deformation basis to start frame. And I'm going to switch to custom attribute node. And now I've assigned some custom attributes already within this node group. And one of these is that sign distance value. The final thing we need to do is click this button, which connects all the points. And you can see this looks like a mess right now. All we need is some kind of face corner attribute for each vertex. So it doesn't matter how these points are connected as long as they're connected. And this is just so those points can be represented in a UV map. So now again, I'm not going to use single row mode. I am only encoding that sign distance value to the red channel, and I can encode this as a vertex animation texture. So when this finishes, we'll have something that looks like this. It looks very distorted and looks like something went wrong, but it didn't actually. Our encoding just assumes that what we wanted was to represent this as positions. But before I go into correcting that, let's go ahead and encode the normal. So again, I already have custom attributes assigned for gathering this normal information from the original mesh. I'm going to hide that result in OpenVAT preview. I renamed this object to volume normal capture, and I'll set my custom attributes to normal X, normal Y, and normal Z. And then I can just encode this again. And that's just because it is normals captured and the result thinks we want position again. To avoid this file running slowly, I'm just going to link this SDF capture VAT into a new scene and name it SDF display. Now, the node group that this is using, OpenVAT decoder, won't really work for us. And I have another method in here that's called OpenVAT decoder Splat. And this will gather the correct information that we need, including the normal texture. If you're using this yourself, you'll need to set the second image property to your captured normal. And then we're going to add to this modifier stack. So we're going to add another geometry node group, and we're going to set its tree to this OpenVAT Splat instance control. Now in the output attributes here, we need to set this to UV map. So based on how I use these signed distance field values and what the scale of these points are, we can get different results. You can see this immediately isn't as clean as the mesh-based reconstruction, but can still be really useful in some scenarios. And because we're using that normal information in the mesh, we can actually almost get a 3D representation of this. Now, in my scene right now, all the planes are facing forward, but they really need to follow the camera. So I have this helper panel, which will do that for us. It creates a tracker based on the viewport's location and updates it continuously so that no matter where we're viewing this from, we can get a representation like you would see particles in a game engine. If I play with the signed distance field value, we can try to get a tighter representation of this. And honestly, I probably should have used more points for this, but since this simulation is so big, I didn't want like a 4K Vertex Animation Texture. It would have just taken too long to render for this example. But it is totally feasible, depending on if your system can handle encoding something that big. But this can also be good for stylized effects. Like if you wanted something like this, it kind of looks like a rendered point grid because it is. And this could totally be refined a lot by systems like Niagara. You could even just use these points to drive your Niagara simulation and not use these points identically. But you're basically getting a voxel representation or a signed distance field representation of your animation over time. I hope that this has been interesting to you. This is something that I've been working on for a long time. Both of these are techniques that I haven't seen anywhere else. I'd be really interested if anyone has any information of other people doing things like this. This might not be the preferred way to get fluid simulations into Engine, but this is an extremely CPU efficient way to get simulations into Engine. Obviously, these simulations have to be baked, so you can't get real runtime interaction with, say, a character. You can fake some things, which I'll show in future videos, of like ripples following around a character. But fluid simulations that run in Engine inherently use a lot of CPU to do the calculations of the fluid. And the only way to really get baked simulations into Engine is with cached mesh sequences or volume textures that are sequences, which can be really heavy because you saw when I was doing the SDF volume, how many voxels essentially I needed to create something that looked decent. A volume texture would need that same amount of voxel information, at least per pixel. Unreal does a sparse representation with SVTs. So I'm not trying to say that this is the best or the only way to get fluid simulations into a game engine. So theoretically, these can run on mobile. This would be an uncompressed 16-bit texture at the minimum. So the memory requirement is a little higher than you would want for a mobile game, but not unreasonable by any means. Leave a like if you thought it was interesting. Subscribe if you like this kind of content. Grab the files on GitHub, and I'll see you in the next video.